This visual represents an absolute coordinate system. Every single position on this grid is defined by strict, intersecting orthogonal lines. Plotting a point P at exactly 3, 4, we face a mechanical problem, finding the length of the diagonal segment connecting it straight back to the origin, O. The grid itself does not measure diagonals. Its native measuring tools are strictly horizontal and vertical. If a point lies flatly on the x-axis at 3, 0, calculating the length is a simple counting exercise. The same logic applies to the y-axis. But when a line cuts across the grid, neither axis gives us the measurement. Our native tools offer no direct way to calculate a diagonal trajectory. To measure this empty space, we have to build a bridge between the strict accounting of the coordinate grid and standard Euclidean geometry. We translate this diagonal by projecting point P onto the axes. We drop a perpendicular line straight down to the x-axis, creating a new intersection at 3, 0, labeled Q. By anchoring the point, we construct a right-angled triangle between O, Q, and P. This specific shape triggers a known rule from Euclidean geometry. The Pythagorean theorem states that in a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the other two adjacent sides. Our constructed triangle is built directly into the grid. The horizontal base, OQ, runs along the x-axis, giving it a precise length of exactly 3 units. The vertical leg, QP, runs perfectly parallel to the y-axis, making it 4 units tall. We now set up the Pythagorean equation using these specific geometric segments. The length of the hypotenuse squared is equal to 3 squared plus 4 squared. Executing the calculation, 3 squared gives us 9, and 4 squared 16. Adding them yields 25. Taking the positive square root resolves to final step, revealing the exact linear distance of 5 units. Mathematically, a square root produces a positive and negative number, but physical distance requires a positive value, so we ignore the negative root entirely. The specific coordinates 3 and 4 act as the pre-measured legs of a right-angled triangle hiding on the grid. We found the distance for 3, 4, but we must determine if this process represents a universal mechanical rule or if it relies strictly on these specific numbers. We strip away the numbers to test a purely theoretical point, defined only by variables x and y. Dropping a perpendicular line from point P will hit the x-axis at a horizontal distance of x. The vertical height perfectly matches the vertical coordinate, y. We substitute these variable dimensions straight back into the Pythagorean framework. The resulting generalized rule states that the distance from the origin to any point is simply the square root of x squared plus y squared. Introducing algebraic variables liberates the geometric logic. We can now calculate distance without knowing the exact location of the point in advance. We can expand this framework further to calculate the distance when neither point is anchored to the convenient 0 of the origin. Let us test point P at 5, 6 and point R at -1, 2. We cannot simply drop a perpendicular line to an axis anymore. The base of our required triangle is no longer the axis itself. Instead, we construct a localized, virtual right-angled triangle suspended perfectly between the 2 arbitrary points. We draw a horizontal line rightward from R and a vertical line downward from P. They intersect, forming a perfect 90-degree angle. We deduce the coordinates by borrowing x from P and y from R, locking this new vertex at 5, 2, labeled Q. With the virtual triangle built, we must calculate the specific lengths of its horizontal and vertical legs. We calculate the horizontal base by subtracting the lowest x-coordinate from the highest. Subtracting -1 from 5 yields a total horizontal distance of 6 units. We execute the exact same process for the vertical height, subtracting the lowest y-coordinate from the highest y-coordinate. Subtracting 2 from 6 yields a total vertical distance of 4 units. There is a crucial mathematical caveat here. Because we will eventually square these lengths, the order of subtraction becomes completely irrelevant. Any resulting negative numbers will correct themselves during the squaring process. By combining the x and y coordinates of any 2 points, we forcibly construct the right-angled geometry necessary to measure the space between them. With the legs defined as 6 and 4, we initiate the Pythagorean calculation for diagonal PR. Squaring the horizontal base gives 36, and the vertical height gives 16. Summing these squares yields 52 under the root. Simplifying this mathematical root reveals the exact distance, 2 times the square root of 13. This specific numerical success scales up to a broader academic concept. We can translate this entire multi-step geometric process into a single line of algebra. The equation shown here is the formal distance formula, exactly as it appears in textbooks. It is a formalized set of instructions. The first term in parentheses commands us to calculate the horizontal base of our virtual triangle. The second term instructs us to calculate the vertical height. The overarching square root bracket enclosing the equation is the final execution of Pythagoras, isolating the hypotenuse. Because of the squared terms, the spatial orientation, quadrant placement, or negative coordinates of the points cannot break the formula. The geometry holds firm. The coordinate distance formula translates ancient geometric principles directly into the modern Cartesian plane.